Yeah, this is our final, afternoon session here. So you're almost there. Just a few more exciting talks. And in fact, we'll hear about some very exciting stuff about upcoming missions and what the future holds for demographics. And starting up is going to be Vanessa Bailey from JPL, telling us about Nancy Grace Roman and HWO. Take it away, Vanessa.
So yeah, let's see, where's the best place? Oh, so I should use this so the folks in the back of the room can hear me now. Okay, cool, great. Yeah, I will be thinking towards the next 25 years of Sagan, looking forward to what kinds of exoplanets we might characterize with direct imaging. You've heard a number of really great talks this week. Eric giving the introduction to direct imaging and what we've been doing up till now. You've heard from various folks throughout about the search for life and atmospheric characterization, and then this talk will speak a little bit to where NASA is going with direct imaging, the search for life, and comparative planetology. Again, the theme that emerges again and again is how do we find Earth-like objects, Earth-like planets, solar system-like systems. And in this talk, I'll really be focusing about solar system-like in the very specific sense of having a sun-like host star, not low-mass host stars, but sun-like host stars. And in that sense, that's how we define Earth 2.0 for the context of this talk. And that's that sun-like host star is what's pushing us towards direct imaging, because the habitable zones are so much farther away from their host stars than for the low mass stars, where you can use transits to probe those planets. And because we're talking about direct imaging, although this is a demographics workshop, direct imaging necessarily has a smaller sample size. So I'm not going to wow you with 1,000 direct imaging planets and all of the fantastic demographics you can do with that, but you can still do pretty exciting comparative planetology with a smaller sample size. Yeah. So to find the Earth twin, NASA's taking the approach of using reflected light spectroscopy. This is distinct from direct imaging that Eric mostly talked about earlier in the week, that's emitted infrared light. We're now talking about reflected, visible, and very, very near infrared light from the surfaces or the cloud tops of these planets. Whether that's something that's Earth-like or it's going to work equally well for something that's gaseous. And that is the underpinnings of NASA's Habitable Worlds Observatory mission concept. This is something that will launch maybe 2040s, depending on who you talk to and how optimistic they are, late 2030s. But my money would be on into the 2040s. So something that we're going to be discussing at the next Sagan milestone of Sagan 50. We should hopefully have some really great results from HWO. It's at the mission concept stage. I'm going to be presenting results from and early concept studies from a couple of working groups. This is not my own work, but rather others. And you heard this morning from Jake about the search for life within our galaxy, search for life on terrestrial planets of various sorts. And he's really an expert that I hope you'll take advantage of while he's here. You saw this, I think, these same questions this morning. When you think about the search for life, what are the signs of life? What could mimic the signs of life? How will you know that from imperfect data? And these are the kinds of questions that you have to think about when you're designing a mission, when you're early in a mission concept. HWO aims, we hope, to be able to find life not just like modern Earth, but perhaps like existed on Earth earlier in its life cycle. And again, you saw this, I think, this morning, that the Earth's own atmosphere has evolved significantly over our last few billion years. Modern Earth is a very small fraction of Earth's history, and we can design a mission that's only sensitive to a modern Earth-like planet and life as it currently exists. And that's a perfectly fine mission. It would just be leaving out a lot of Earth's history and leaving out sensitivity to some of the earlier, simpler life forms that were present on the planet in the first couple billion years of life's evolution. And if we want to be sensitive to these various different types of life-hosting planets, that's going to drive us to have multi-wavelength coverage and both imaging and spectral coverage I'm not going to trace down this decision tree that is credit to Amber Young, but here it's simply to point out that if you start with a planet, you maybe first look for water or for methane, and you'll follow a decision tree down depending on what different molecules you see at what abundances in the atmosphere, and that some of these are only obtainable in the visible, some in the infrared, and some in the UV. And we need that broad spectral coverage again because you saw this morning, we have a diversity of atmospheres even in Earth's own history. So, for example, in modern Earth, maybe oxygen presents a fairly deep absorption signature that we can access with just visible light. But earlier in the Proterozoic era, oxygen was pretty weak. It was present, but I'm not sure I'd be able to detect that with a visible light spectrograph at low signal to noise. Instead, maybe you go after something like ozone in the UV, which is a proxy for oxygen. So that drives us, for example, to get UV photometry in addition to visible light spectroscopy. Or you might be interested in comparing Archean Earth to modern Earth. The abundances of methane and carbon dioxide are very different. If you have something that looks like Archean Earth, you actually do start to get absorption features of methane detectable and visible. But if it's at modern Earth levels, probably you need to go out to the infrared. So this is pushing us in a mission concept like HWO to have this broad wavelength coverage. I'll say it's not all worked out yet. There's a lot of smart people thinking about, really what's the minimum wavelength coverage you need, what's the minimum spectral resolution you need to study the types of planets that you want, and how ambitious do we want to be about how much of Earth's lifetime we would be sensitive to. And in putting this sort of in context of the performance relative to other direct imaging missions that exist today, you've seen some version of this flux ratio sensitivity detection limit as a function of projected separation on the sky. Those little red squares at the upper right are those self-luminous planets that have already been detected with current instrumentation. And where HWO wants to go, this Earth-like planet around a sun-like star in our solar neighborhood, you can see is many orders of magnitude lower. And it's designed for this goal. The most stringent driving science goal of HWO is that exo-Earth twin characterization. But I'm going to skip that. But if you can observe an Earth twin, you can also observe a whole lot of other planets. So anything that you design to find life on an Earth twin is going to be very powerful for characterizing the whole zoo of exoplanets in our solar neighborhood. Because, of course, the flux ratio in reflected light is going to increase as the radius of the planet increases. So it's going to be very powerful for studying super Earths, mini Neptunes, gas giant planets at the inner scales of the solar system, at terrestrial scales. And there's again a whole working group of folks thinking about this with HWO. You heard from Jesse this morning in the context of demographics and what makes for a good survey. So pick her brain about the solar systems in context while you got her too. And once we have something that can image an Earth, we can ask a lot of questions. We can study super Earths and mini Neptunes. We can characterize their atmospheres, understand these two classes of populations in the upper right, just showing, an example of the number of super Earths and mini Neptunes you might detect within the habitable zones just in the course of surveying for your small rocky planets. You can start to attack questions on solar system scales of how planets are born, how they evolve. We know that super Earths are the most common planet in the interterrestrial zones. Is that going to be true as we push farther out, and how do their atmospheres compare? But there's one kind of unique challenge as you go to reflected light and as you go to multi-planet systems and at smaller orbital distances. That's sort of new to direct imaging. In the direct imaging systems that we're pretty used to at this point, they're young, self-luminous super Jupiters at very large orbital distances. So they're, excuse me, so their fluxes are more or less constant in time. There's some small variability, but largely constant in time. And there's no orbital phase variation, so you can observe them anywhere in their orbit. The only thing that matters is projected separation. That's no longer true, right? Once you're looking at reflected light, the planets will only be illuminated when they're on the far side of the star from you. So their flux is time variable. And we hope we're pushing it towards an era where we can image multi-planet systems. Yes, we have HRID 799 in the self-luminous planet world, but it's very obvious. You can see all 4 of those planets at once. Each one of them has very long orbital timescales, and so there's no confusion. But if we look at a simulation of what you might see in our own solar system with a reflected light observation, you can see Earth and Venus orbiting quite close to that central occulter, Jupiter and Saturn more distantly. Imagine only getting a snapshot of that once or twice or 3 times over the course of a couple years. It's not trivial if nobody's sitting there with a little marker telling you which planet is which, to know, especially within the terrestrial zone, that you have 2 planets there, Earth and Venus. You might confuse them depending on when you observe. And you can see here as time progresses, Jupiter and Saturn are completely invisible because they're on the wrong side of the sun. So our sensitivity depends on when we observe it and what kind of planets we're observing, which is just an additional layer of complexity in scheduling and interpreting our observations. One, if we think about this deconfusion problem of, we have, say, 3 epochs of imaging in photometry, and we want to understand, which planets are we imaging at a given time. It's not trivial. Here's an example simulated observation over 3 epochs. The epochs are coded in different symbols, but I would challenge you to be able to, by eye, tell which of those points goes with which planet at which time. It's not trivial. So now we have to figure out ways to deconfuse those signals. And this is something that I wanted to highlight. Grad student Sammy Hassler just defended her thesis this morning, and here is a plot from work that she's been doing on deconfusing these planets. So congrats, Sammy, really awesome work. You can try to deconfuse planets by making sure that whatever orbits you fit are dynamically stable. You can add multi-band photometry, so that might help you distinguish, say, between Venus and Earth. Of course, the holy grail is if you also have radial velocity constraints, but we've all heard how weak those radial velocity signals are for the lowest mass planets in the system, or the more distant ones. So radial velocity isn't always available, but it's about taking any and all information that you have to deconfuse the signals that you're observing. And understanding and constraining the orbits will help with optimal scheduling now to make sure that you're observing when the planet will, taking your spectrum when it will be bright enough to have high signal to noise. So these are all new problems that we're going to encounter just from the observational design standpoint. From the technology development standpoint, there's a lot of work to go. I won't get into that in detail today, but we know that we're going to need multi-wavelength, all the way from UV to near IR coverage. That's not possible with a single instrument. That it's just not possible to design one instrument that will suppress starlight simultaneously across that broad bandpass. HWO, therefore, is looking at several different parallel channels. The starlight suppression technology itself is still a couple orders of magnitude beyond what's currently flying in space. There's a lot of telescope stability, starlight suppression technical problems to go that I won't get into, but if you're interested, there's another conference next week that will be streaming its plenaries online for free. So if you want to learn more about the science behind Habitable Worlds Observatory or some of the technical challenges and proposed solutions, I really encourage you to tune into that talk. And then I want to transition for the second half of my talk to the kind of the intermediate step. Like that's NASA's long-term goal, 2040s, next Sagan workshop milestone. What are we doing to get ourselves there? How are we bridging the gap between our current capabilities and that 10 to the minus 10? And this is where the Nancy Grace Roman Space Telescope comes into the picture, launching possibly as soon as September of 2026. So really coming right up. Um, it's got two instruments. You've already heard quite a lot from various speakers about its microlensing and transit capabilities using the wide field instrument. And the other instrument on board this observatory is the coronagraph instrument. And that's what I'll be speaking to for the rest of this talk. This is a photo from a couple weeks ago now. The solar panels are actually installed. The observatory is going into the vacuum chamber, getting ready for some of its final testing over the course of the next couple months. And this is all happening at Goddard. So where is the Roman coronagraph in the context of this big picture? With our pre-delivery instrument testing, before it was integrated into the spacecraft, it got to contrast levels of a few times 10 to the minus 8 just in lab testing. That we don't think that's the final performance limit for various reasons, just to do with the time and conditions available to us during testing. We can extrapolate with the instrument models and suggest that long exposures should get us down, we hope, to a few times 10 to the minus 9 contrast. Again, still, more than an order of magnitude away from HWO, but making a lot of progress technologically towards that goal. For context, I'm just showing a few gray triangles here. These are some known radial velocity Jupiter-like planets with some predictions for how bright they might be in reflected visible light. And you can see we just start to skim the surface. So Roman coronagraph is designed as a technology precursor for habitable worlds rather than primarily as a science instrument. And our main purpose here is to prove out a fair number of different technologies that we think something like habitable worlds might need, but have never been proven in space up till now. So that's active wavefront control, so precisely counteracting optical aberrations in the system, to combined with coronagraph masks that are very specifically designed for the complicated pupil of the telescope. Together, these things suppress the starlight by a factor of 100 million or so. Once you've suppressed the starlight, can see these very faint signals, you're actually receiving only like one photon every few seconds, one photon a minute from a planet per pixel. You need incredibly low noise detectors. So this electron multiplying CCDs are something that are being used in space for the first time in this regime. And HWO will need even lower noise detectors as it pushes even fainter. If you want to learn more about the technologies behind Roman coronagraph, there's a special edition of JADIS that just came out that has about the first half of our papers, and we'll have some more coming out over the next couple months. We are going to have, being a technology demonstrator rather than a science instrument is a little bit different flavor than folks may be used to in dealing with, NIRCam on JWST or STIS on HST. We have only one required observing mode, which is a 575 nanometer centered bandpass with narrow field of view imaging. But then there's a few extra capabilities that are built into the hardware that aren't officially fully supported. But we hope to be able to commission those reasonably early on in the mission, but we call them best effort, formally speaking. If you want to see more about the full list of hardware that's installed, all the possible filter coronagraph combinations, AJ Riggs has just written a paper in that JADIS special issue. And with that, again, our primary goal is to mature those technologies, but we're going to get 2,200 hours of telescope time to test them. That's all overheads included. It's not just 2,200 hours of open shutter science time, but it's nothing to sneeze at. And so we'll check out the technology, we'll operate on bright stars, and then with whatever time we've got left, that's time for additional science. That's time for additional technology tests. And one important thing I really want to stress is that Roman as a mission is doing something new. There's no proprietary period on any data coming out of the the Roman chronograph instrument or the Roman wide field instrument, at least after our initial commissioning period's done, which is only the first couple months of the mission. So this data will all be immediately available for you to play with. And we imagine we are going to be observing these young self-luminous super Jupiters, but at visible light, at shorter wavelengths, accessing different molecules, trying to better constrain abundances and cloud properties through a combination of near IR and visible light imaging. We can imagine that we hope with the predicted performance will let us take the first actual image and first low resolution spectrum of a true cold Jupiter analog in reflected light, and broadly answer whether maybe is that a cloudy or a clear atmosphere, and are we kind of solar-like abundance? Are we super solar abundance? There's only a handful of systems where this might be possible, but I'm really excited for this potential first out of roaming in the next couple of years. It's not just exoplanets. I know this is an exoplanet conference, but it's also about exoplanets in the context of the entire system. So I'm pretty excited as well about the debris disk and exozodi science that we think we can do with Roman chronograph. So this image here is a Hubble Space Telescope image of an edge-on disk, and that black bar in the center is just a region where the chronograph performance wasn't high enough to be able to access. And that's basically our entire field of view for Roman. So we'll be very complementary to Hubble. James Webb, it's sort of a similar picture. And we're complementary to the ground as well, because we'll be able to access fainter surface brightness disks and more extended disk morphology compared to the ground. So it's not that it replaces, but it complements. And then, hopefully with our multi-band photometry, with our polarimetric capabilities, we can start to study some grain porosity and broad grain composition. And again, where we might really complement what's available right now is the sensitivity to terrestrial zone dust, or exozodi. So one of the things that we worry about for a mission like Habitable Worlds Observatory is whether there's so much dust in the terrestrial zone that it might actually obscure the planets. That cartoon there is showing a dusty and a clean system. There've been precursor surveys in the infrared to look for this dust with the infrared emission. The Large Molecular Telescope Interferometer conducted the host survey, and we know that on average most systems are fairly clean, but their upper limits on the stars that HWO is most interested in might be something we can improve on with actual visible light images with Roman chronograph as kind of a reconnaissance survey. And those are flavors of science that I'm excited about doing with Roman chronograph, but I also really want to highlight that we want to hear from all of you. What are you interested in doing with Roman chronograph? Since we're a tech demo, we don't have an open geo program in the way that you're used to, but we have no proprietary period. So what we're doing is opening a white paper call for people's concepts. So this is, what would you like us to design and observe with Roman? We want this to be pretty low-hanging fruit. So it's like 1 page of science justification, 1 page of an observation description, due on August 7th. And we want to hear from anybody and everybody. You can send us your qualitative ideas. You could send us what's your favorite target that you really want us to observe. We want to hear from you. So I hope you'll take a look at the white paper call or at romanchronograph.space, and hope to hear from you. So in summary, I've talked a bit about a couple missions that NASA's working on towards finding life around Earth-like, around sun-like stars on Earth-like planets. Eventually, we want to get to Habitable Worlds Observatory at the 10 billion to 1 starlight suppression, but we're going to start with Roman chronograph at the 10 million, 100 million, maybe even a few hundred million starlight suppression level that I think may give us the first opportunity to look at a true cold Jupiter analog and maybe terrestrial's own exozody dust for the first time. And we want to hear from you. I'll just emphasize that again. We want to hear from you, even early career for folks. Please submit your white papers.
All right. Thank you, Vanessa, for that great talk. We have time for a few questions.
And if you're in the room and you ask a question, you can come pick up a sticker afterwards.
So while you all race to the microphones, a couple questions from online. So the narrow wavelength range of Roman, how were those wavelength channels chosen?
Yeah, so I alluded to this a little bit at the beginning with HWO that you can't have one instrument that covers too broad a range of wavelengths. And that just has to do with the starlight suppression instrumentation design. That something you optimize for UV won't necessarily work in the visible, something that works in the visible may not work in the infrared. So you tend to choose a broad range of wavelengths in that way. But more specifically, there's an interesting methane feature in gas giant atmospheres around 730 nanometers. That's why we chose that for our spectroscopy band. And then just trying to push as far to the red and as far to the blue as we can, 525 and 825 for, say, the disk color imaging for grain properties. And you're playing a balance between trying to get as much wavelength coverage as you can while understanding if you try to cover too much ground at once, your overall performance is going to be poorer.
All right. Thank you. And once again, these are up for grabs if you just come and ask a question. All right. So while that happens, I will ask a question. So you showed a chart of about four technology demonstrators for Roman that's going to be tested for the first time in space. And I'm going to ask you to predict the future.
Mhm.
Which one of those do you think is going to be the most difficult, most uncertain at this point?
Oh, so for Roman, for a long time, I was in a lot of ways the most worried about the EMCCD and radiation damage to that because when a cosmic ray hits a detector, a CCD works and it has a high readout efficiency only if all of the atoms in that lattice are well aligned. And you can be hit by a cosmic ray, knock an atom out of alignment, and that'll reduce your sensitivity, to reduce your ability to detect and shuffle charge off the array. So for a while, there was a concern that our susceptibility to radiation damage was going to be our life limiting factor. So there was quite a bit of R&D put in to developing a radiation hardened EMCCD plus encircling it in a giant hunk of tungsten shielding. That helps as well. So that was for a while something I was the most worried about, and that's kind of leveled out to comparable level of worry to the other technologies. Now the thing that a choice that we made to keep ourselves within our cost and schedule limits was to make ourselves single string. So we're not redundant in the way that a typical what we call Class A instrument that you're used to on a flagship is redundant. So if any one of these components fails for some reason, that will be the end of the instrument. So I think that's now kind of probably the thing I'm most worried about is just what's the low probability event that will eventually end our observing lifetime. But we designed for a multi-year lifetime. So I think the likelihood of an early failure is pretty low.
Nice. All right. Thank you. All right. So in the interest of time, why don't we go ahead and move on to our next speaker? Let's everyone thank Vanessa again.